All right, so this lesson we're going to be working on exponential functions. An exponential function is a function of the form f of x equal b to the x, where b is greater than 0 and b is not equal to 1. b equals 0 and b equal 1 would create constant functions, and I'm sure you can imagine all the craziness that would happen if b were negative. So, if b is greater than 1, for example, it's going to look something like this. This function is f of x equal 2 to the x, and this is an example of exponential growth. In this function, you can see the domain is all real numbers because you can take 2 and raise it to any power. The range is y has got to be greater than 0 because you cannot produce any negative numbers or 0 out of that expression. It is increasing because b is greater than 1. There's a horizontal asymptote at y equals 0, which as x approaches negative infinity, you can see that this is going to get closer and closer to that x-axis. And the y-intercept is going to be 1 because anything raised to the 0 power is 1, and that's going to be true of all of our standard parent exponential functions. If we change the base to, say, 3, for example, f of x equal 3 to the x, we get a function that looks like this. What you'll notice is it just is steeper. The domain is exactly the same, range is the same, it is still increasing, but increasing more quickly because the base is greater than 2. Base is 3 in this one. Still has a horizontal asymptote y equals 0, and still has a y-intercept of 1, because anything raised to the 0 power is 1. Now, if b is between 0 and 1, let's say, for example, a function that looks like this, f of x equal 1/2 raised to the x, our function is going to look like this. And what you're going to notice about this one is everything else is exactly the same except for the fact that instead of increasing now, it is decreasing. So it is a decreasing function when b is between 0 and 1. And that is called exponential decay. But you'll notice the horizontal asymptote still y equals 0 because as x approaches infinity, this function is going to approach that x-axis again, or the line y equals 0. Y-intercept is still 1 because 1/2 to the 0 is 1, and domain and range are still exactly the same. You may have also observed that this red one and this green one are horizontal reflections of each other. That probably won't surprise you because you know that 1/2 raised to the x power is the same thing as 2 to the negative 1 to the x power is the same thing as 2 to the negative x power. So the function 1/2 to the x is the same thing as 2 to the x with a horizontal reflection there. And that's why they're horizontal reflections of each other. Now suppose you wanted to graph an exponential function that's a lot more complex. This one, the parent curve is 2 to the x. That's what we have drawn here in red. It's 2 to the x. So you could apply this vertical stretch of 3 and this horizontal translation of 3 and this vertical translation down 4 to whatever you would consider the key points of this thing, just like we did with all the other functions that we used to use. But the truth is, it may be better just to have a very good sense of what this looks like and then plot some points. For example, the horizontal asymptote here at y equals 0 is only ever affected by a vertical translation. So since we know the vertical translation is down 4, we know that there is a horizontal asymptote at y equal negative 4. So we know there's a horizontal asymptote right there at y equal negative 4. Now, we also know that this is exponential growth because my base is greater than 1. And because there are no reflections of any sort, vertical or horizontal. Okay, so now what we could do is we could just plug in some values for x, essentially do a table of values. For example, if I wanted to know what f of 3 is, f of 3, I just plug it in there. I get 3 times 2 to the 3 minus 3 minus 4, which is 3 times 1 minus 4, which is negative 1. So I have the point 3, negative 1. So I know 3, negative 1 is on my curve. I also know if I were to plug in, say, a 2, f of 2, I get 3 times 2 to the 2 minus 3 minus 4, which turns out to be negative 5 halves. So I also know I have the point 2, negative 5 halves on my curve. And that really is probably enough to graph your curve, and it's going to look something like that. Now, if it's me taking a test, I will probably plug in a couple more values like 4 and maybe 1. So that's how you graph an exponential function. Let's see how to find an exponential function's equation from a graph. Okay. So let's take a look at this one. Pause the video if you'd like and see if you can try to figure out how to find the equation of that graph. Sir, there are too many things to figure out. There are all those vertical transformations and horizontal transformations. You don't even know what the parent curve is. I mean, what's the base? Yes, if we write f of x equal a times b to the c x plus d plus e, we have vertical transformations, horizontal transformations, and a base in there. That's 5 things to figure out. That's more than we normally have to figure out even. So, well, I'm going to show you something cool that's really going to help. So we got vertical things and horizontal things going on here. But what I'm going to do is I'm going to use my rules of exponents to rearrange this a little bit. This big complicated thing can be written as a times b to the c raised to the x plus d plus e. That's my power to a power rule there. Now I'm going to use my product rule, and I'm going to write this as a times b to the c to the x times b to the c to the d plus e. And then I'm just going to move this little bit over here, and so I'm going to rewrite it as a times b to the c all raised to the d times b to the c raised to the x plus e. Now, this looks super complicated, but what I want you to notice is there are no more horizontal transformations on it whatsoever. The base is now this b to the c part. This is a vertical translation, and this awful looking thing right here, which is really just a number, is the vertical stretch or compression. So no more horizontal transformations. Now, why is that important? Well, that's important because it means that absolutely every single exponential function can be written solely using vertical transformations. Take a look at that. Instead of 5 things to figure out, now we really only have 3 things to figure out. And that is going to make our life so much easier. So what you should notice here is that the horizontal asymptote is only ever affected by that vertical translation. So the horizontal asymptote is always going to be equal to y equals c. And, you know, the y-intercept occurs when x is 0, and we know that anything to the 0 power is 1, so the y-intercept is always going to be a plus c, so you're always going to have that point 0, a plus c. And that'll help you find a and c, so the only thing left to find now is b, and so all you'll need now is one more point, and that should help you find b. So now let's take a look at our function that we're given here. The horizontal asymptote clearly appears to be y equal -1, so that tells me that c is equal to -1. Okay? And I could go ahead and write my equation this way, a times b to the x minus 1. 2 more things to find out. The y-intercept is 0, -1/2, so I'm going to put f of 0 in here, and that's going to give me a times b to the 0 minus 1, and f of 0 we said is -1/2, equal a, b to the 0 is 1 minus 1, adding 1 to both sides, we get a is equal to 1/2. So I know c is -1 and a is 1/2. I could also have gone with the fact that the y-intercept is always going to be a plus c, and I could have just said, well, the y-intercept is -1/2, and a is what I'm trying to figure out, and c is -1, and then solve the equation this way. Those are essentially doing the same thing, though. And now I only have one thing left to figure out, because I have y equal 1/2 times b to the x minus 1. And I have this extra point here, 2, 3.5. So I put a 3.5 in for y, a 2 in for x, adding 1 to both sides, multiplying both sides by 2, I get 9 is equal to b squared. Square rooting both sides, I get b is equal to plus or minus 3. We've already established that you can't have a negative base, therefore b is equal to 3. So in the end, I get the equation f of x equal 1/2 times 3 raised to the x minus 1. And that is how to find the equation of an exponential function. Okay, let's try to find another. Have a look at this one. Feel free to stop the video and go ahead and try to figure out the equation of this exponential function. Okay, let's see how you did. All right, this is my general function right here. I know that c is 7 because the horizontal asymptote here is 7. I know that makes a -2 because a plus c has got to be equal to that y-intercept, which is 5. So that's where I get my a is -2. And then plugging in the point 1, -3, which I can find right here, I solve for b and I get b is equal to 5. And so your function is -2 times 5 to the x plus 7. I should point out that sometimes they won't give us the y-intercept, but as long as they give us 2 points, we're okay. Because we can get to this stage, the same thing, getting that c value simply with the horizontal asymptote. Now what I have is 2 variables. So if I have 2 points, I know that when x is 1, then y is -3. And I also know that when x is 1/2, y is 2.5. And now what I have is a system of equations, so 2 variables and 2 unknowns. And you can solve that just using your algebra for system of equations. Okay, now that we've done exponential equations and we've done exponential functions, we're going to work on the applications of exponential functions. Have a look at this problem and see if you can do it. So this is exponential because there's a 3% growth rate per year. So each year is going to be 103% of the previous year. So you're going to have to multiply by 1.03, and then the next year by 1.03 again, and then again, and then again, and that's what makes it exponential. So this is your model. So if you want to know the predicted population in 5 years, that's P of 5. So you just plug in a 5 and evaluate. 34,778 people. No real good reason, since it's a math model, to round to the person. So I rounded to the hundreds of people. And then when will the population reach 100,000? This time you let 100,000 in for your population, and now I get a chance to use logs, which is great. So I divide both sides by 30,000. Then I take log base 1.03 of both sides, and so I get t is equal to approximately 40.73 years, or about 41 years. Let's try another one. Have a look at this problem. So in this problem, it says only 10% of the light is blocked out. Okay, so what that means is 90% makes it through. This is a good example of exponential decay, right? Because b is less than 1. So how much makes it through for 5 millimeters? Well, 90% of 90% of 90% of 90% of 90%. So 0.9 raised to the 5th power. That's going to leave us with 0.590. So approximately 59% of the light is making it through. So that's your exponential functions and applications. Now, go enjoy some homework.